a system which had no rotating seal in it. Previous systems had rotating seals. Now, he changed the system a little bit again, and this time, instead of causing the rotation of the planet to occur through use of a pulley, he used a gear in the center and then a gear on the pulley, the gears being identical size. The pulleys were also identical size earlier. Now, this, as you'll see as I go on, is a vastly different type of instrument. It's surprising that every other feature of the instrument is kept the same, except you have 2 gears instead of 2 pulleys, and yet it completely changes the nature of the force field in the system. However, it's also a system which doesn't require a rotating seal. And I'll pass around this model, and this is a model of the J machine, and it's indicated on the base here that this is a J. It's gone through different names. You'll see different names on the base of this, but currently it's called a J type. And this one that I'm showing you now has an eccentric column on it, the same as we just described for the I system. And you'll see the way the leads go through, and you'll see that as you rotate this, the leads leapfrog over one another. This is the incoming and outgoing lead, and they attach to the coil here. But you see, they don't twist. They just leapfrog over one another and remain anti-twisting. So he investigated this type machine starting in the late 70s, actually. And it too, the way he was then investigating it, did not lead to high retention of stationary phase. But there's renewed interest in the I machine now compared to the 80s. Ito mainly pursued the J type from about 1980 on, even though initially it didn't produce a high stationary phase retention. But now there's renewed interest in both machines, and that's why I wanted to describe both, because some of it has to do with the relationship to the stationary force field. And I'll pass that around to people. Now, however, I just mentioned that with the eccentric coils, and even also with concentric coils, concentric with the planetary axis, the stationary phase retention was not that great. So Ito thought about finding a way to increase the retention of the stationary phase. Now, and what he came up with was to, instead of making a simple helical coil, which all the machines up to then consisted of, he made what became called a multi-layer coil, where he wound the coil on a spool which started at about 4 inches in the internal diameter of the spool, and could be extended outward to about almost the radius, which in the instrument he made was a radius of about 10 centimeters. And so that created a centrifugal force field within the coil itself and tended to pull the heavy phase toward the outside of the coil. And it was best usually to arrange it so that the head of the coil was actually at the center, and the heavy phase in that case tended to go toward the tail. In both cases, the heavy phase tended to go toward the tail. But this accelerated its travel toward the tail. And I'll pass this model around, which is the same as the previous one, except for the placement of the coil. And you see this is a multi-layer coil, now wound concentric with the planet axis. And you can see how it moves and how it's anti-twisting. Okay, now let's go on to the projector again. All right, I described before that Ito went to a multi-layer coil, and that's indicated here by a single spiral, but in a multi-layer configuration. And we can see what happens now when we have two gears instead of two pulleys. If I move this to the right, and notice, well, you'll see that the coil rotates. It's also rotating in the same direction now that I'm turning the rotor here in the center. And another thing you can notice is if you look at the top of the coil here, then you see when we get halfway around, that's on the top again. So in my opinion, viewing it from here, that rotated once on its axis. And if we go again, it rotated a second time. So I've always said this rotates twice on its axis as it goes around. Now actually, that turns out to be important for the anti-twisting aspect of the device. And you can demonstrate that on this device as well as the model that I sent around. If I hook two tubes on there, then as this goes around, it does the same thing as the model. The tubes leapfrog over one another and they don't twist. So there, it's important that in fact there are two revolutions. However, in the kinematic studies of this, you'll find that they say it rotates once in each revolution. And as it'll turn out, that has something to do with the rotating centrifugal force field. But let me show you what we see. Now, what you might expect in this, if the red phase was the heavy phase and the yellow the light, you might expect to see something like this, where the heavy phase is thrown to the outside and the lighter phase in the middle. That's not what we see. When we did experiments where the phases were dyed, Ito did the original experiments, and he and I did some photographic studies also. And what you see now is that it's strongly mixing in this area, but not the same as before. Before we had what we called cascade mixing, where heavy phase is being carried up and thrown over like a waterfall. But here we see a wave that's formed down here in this part of the apparatus. And this is very peculiar. Now the other thing about this apparatus is it holds, with many systems, as much as 90% or more of the stationary phase in the coil. And it gives remarkable separations. So this was a great deal more successful at doing separations than any device that Ito had made up to this time. This was made in about 1980. Now, let me jump ahead of the story a little bit and put here on top of this the force field that we see. And this can be calculated by kinematic analysis. The force field is completely different from what we saw before. And you see the vectors all tend to go outward. This vector is the strongest vector. This vector is the weakest vector pointing toward the solar axis. This pointing away from the solar axis. They get progressively weaker as we go down here until we get to that. And they get stronger again going up to here. It's rather complicated because they bend in the sense, they tilt with respect to the coil. If you were to look at the tangent to the coil for each vector, you would see that they first bend in one direction, then they go back in the other direction. Very unusual. Now, it also happens that as this rotates, the force field now rotates with the frame of the machine, and so the mixing field remains in the central part of the machine. And the mixing always occurs in the area beneath these opposed vectors. These two vectors oppose one another here. And you notice another peculiar thing, which wasn't obvious, at least to me at the time that we first found this out. We painstakingly calculated the angle of all these vectors. Actually, there's a point here. And if you look at the vectors, you see they all intersect at that point. And it turns out that's a point of zero gravity. It doesn't seem to be useful for doing studies of that sort because it moves. And so you can't put anything there and have it stay there. It moves away. But it is a point where there's zero gravity. And those are the vectors opposing zero gravity. There are a number of other peculiar things in this. Now, it turns out, I mentioned before for the other machine, the eye machine, that if it had a 10 centimeter radius here and it rotated at 800 RPM, that the force field would be 72 times gravity at this point. That's true here, too. If this had those dimensions and that speed, right here, that would also be 72 times gravity. And also it turns out this vector is 72 times gravity, but in the opposite direction. I've done some other calculations recently to show that there are other vectors here which go, let's see, they go, if you look at the tangential force along this line, you get vectors that go up that way. And it turns out they're 72 also, so it's very peculiar. But they're much stronger, whereas this is 72. This one is almost 300 times gravity at the speeds that I mentioned. Now, let me indicate a couple of other features of this. There doesn't seem to be any good sequence to do this in. But let me put down another force field on top of that one. This one is the force field at 0.5, and this is a scale diagram. And that's the force field at 0.5 beta. Let me superimpose on that the force field at 0.85 beta. And you see this is enormously greater. I've forgotten the actual, well, the actual figure is going to be several hundred times gravity at any rate at that point. So you see the field changes with beta in this case, whereas with the eye machine, field remained exactly the same no matter where you put the point. And but all of the vectors, these vectors as well as the ones they had earlier, they all go through that point of zero gravity. Now it's interesting too to look at the way these points migrate on this type I machine or type J machine as the coil goes around. And just for comparison, I'll put on here, whoops, I took one too many off. Let me put on there the same set of points that I used before and line it up so that they're pointing that way. And now let me show you the path that these take. Yeah, I think that's lined up pretty close. You'll see where they go. Now look first at the 0.85 point, which is the farthest one out, the red point and the red line. And you see that as this goes around, now it's going on a really complicated path. It's going around, now it takes a loop, goes around the loop, and actually goes back up. So that's why you get only, well, it turns out if I didn't say so before, it's rotating once with respect to the force field, or once with respect to the rotating frame. And part of the reason for the difference between 2 and 1 is going backwards here when it goes through that little loop, at least at 0.85. Now, if you look at the other points, for instance, the 0.5, which was the one I showed you the mixing for, the green line, that doesn't make the loop. It goes around the green line there. It just comes to a point and then quickly reverses and goes back around. The orange line, which is 0.25 beta, actually goes around and makes kind of a flattened circle. That way it doesn't have a loop or anything. Now, it turns out that point of zero gravity is there. It's on that orange line right there. If you change things and go below 0.25, you get a different situation, which I won't go into. But so the multi-layer coil only works well from 0.5 up to about 0.85 or so is as high as you can go, and you will hit the central axis if you go beyond that. Okay, I think yeah, I think I did point out earlier, this is rotating in the same direction as the machine is rotating, and rotating only once on its axis relative to the force field. Now let me show you the process of countercurrent chromatography using what I like to call my projectable countercurrent chromatograph, where we have a reservoir here filled with a mobile phase, red, and that can be pumped, and a column, which is represented by this short column here, which is filled with stationary phase. And as we pump the mobile phase, we'll reach a point where now the mobile phase has passed through the column, and that amount of mobile phase that's entered the column at that point and is about to emerge is equivalent to the mobile phase volume of the column. This remaining volume in the column will be the stationary phase volume. Now that will come out, and then it will continue. Now let me change the slide that's in there and put in this one. Which begins looking just like the one I had before, but now I've got it marked. That's the mobile phase volume. As that comes out, we will see the stationary or the mobile phase now starting to come out. So it displaced an amount of stationary phase equal to the mobile phase volume. Now, if we had put into the unit something which is not retained in the stationary phase, we would see a peak at that point. And there are several substances we could use to do that, just something that doesn't dissolve in this phase, only goes in this phase. That would mark the K equals 0. Usually there's enough dirty material in the sample that it shows a little peak there. Now, if we continue, we would eventually see another peak coming out. Now, at this point, we've put through the column one column volume, this whole volume of mobile of phase, and we've emerged from the column here with one stationary phase volume. That amount, first mobile phase volume came out, and we saw the beginning of the stationary, or beginning of this was stationary phase that came out, but equivalent to a mobile phase volume. Then we saw the actual mobile phase coming out, and now when we get to a column volume, the sum of those two, we see something coming out, K equals 1, where K is a partition coefficient. And then we keep going, and when another stationary phase volume comes out, we see K equals 2 at a stationary phase volume later. And if we continue again, we'll see, well, I don't have it on here, but we would see K equals 3 at another stationary phase volume. And if you remember, those fundamental facts, you already have the equation for countercurrent chromatography, and that is this. And here. We have the retention volume of an unknown peak. Let's say this is an unknown peak. The retention volume of that will be the sum of the mobile phase volume, which is going to be the same for everything, plus K times the stationary phase volume that came out here, that much. And where K is the partition coefficient. And if you just remember the fundamental facts about 0 comes out with mobile phase front, 1 comes out with the column volume, 2 comes out as stationary phase volume, you can write down the equation just intuitively. And so it's a very simple process, much simpler to explain than solid phase chromatography. And yet the equations really apply to both, except in solid phase chromatography, you don't know the stationary phase volume. You only know the mobile phase volume. So in countercurrent, you know both, and so you can calculate more things. So I mentioned the importance of the stationary phase volume, and I can illustrate that with this movable slide. If you look at the top here, I've got this same kind of column illustrated with mobile phase flowing through it. And down here, I've got a chromatogram which is set so that the peak is coming out at volume is equal to 0. Now, that's because there's no stationary phase there. If we put in some stationary phase, like this, we begin to see peaks coming out. Now, the thing with K equals 0 still is coming out at one mobile phase volume. But as we increase the amount of stationary phase here, you see the peaks spread apart. And so that's why it's important to have high stationary phase retention, because the higher the stationary phase retention, the greater will be the separation between these peaks, and the better will be the resolution, until, of course, we get to the column, which is almost filled. If we have it all filled, then that would be the maximum resolution we could get from that particular system, and it would be spread out such as this. One is still coming out with one stationary phase volume, but the others, one is at 0. And you can look at this and you can say, well, if something came out here, that would be a partition coefficient of 0.5. If it came out here, it would be 2.5. You can see, just looking at the chromatogram, what the partition coefficient is. And the partition coefficient, of course, is the concentration in stationary phase divided by the concentration in mobile phase for the analyte, whatever one it is that you're considering. Now, when I say the concentration, that means the total concentration. If it's an ionizable substance,